The evolution of protoplanetary disks spans several distinct stages, from initial formation to eventual dispersal, collectively transforming diffuse interstellar matter into structured planetary systems. This comprehensive examination reveals the complex processes involved in this remarkable astronomical journey. The journey of a protoplanetary disk begins with the gravitational collapse of a molecular cloud core, predominantly composed of molecular hydrogen. When a portion of such a cloud reaches a critical density or mass, it begins to collapse under its own gravity. As described in Larson's pioneering work from 1969, this initial collapse progresses isothermally, with dust grains efficiently radiating away compressive heating in the infrared spectrum. The collapsing process follows a two-step evolutionary sequence. First, as the density increases, the cloud becomes optically thick, inhibiting radiative cooling, and leading to the formation of a first Larsen core in hydrostatic equilibrium, with a radius of approximately 5 astronomical units, AU. This core continues contracting until reaching temperatures around 2000 K, triggering the dissociation of molecular hydrogen, an endothermic process consuming the compressive energy. This leads to a second, more violent collapse, resulting in the formation of the second Larsen core, the protostar itself, with a radius of about 0.01 AU. A crucial aspect of this collapse is the conservation of angular momentum, which causes rotation to accelerate as the cloud contracts. This increasing rotation forces the cloud to flatten into a disk-like structure, as centripetal acceleration from orbital motion counters gravitational pull in the radial direction while allowing collapse along the axial dimension. The initial collapse phase typically spans about 100,000 years, culminating in the emergence of a central protostar surrounded by a circumstellar disk. During this formation period, the distribution of angular momentum within the collapsing cloud is particularly important, as it determines whether a stable disk can form. The removal of angular momentum to the periphery is necessary for the formation of both the star and its protoplanetary disk. This early disk begins to form during the growth stage of the stellar light core and subsequently expands. The process of disk formation occurs while still embedded within the contracting protosolar nebula, with nebula matter, both gas and dust, accreting onto both the forming star and the disk. Material near the equatorial plane encounters the face of the disk, with turbulence causing the accreting matter to mix with existing disk material. This mixing is particularly effective at the disk surface, where matter falls almost perpendicular, creating shock waves that retard the material long enough for effective incorporation. Near-sound turbulence can produce disk growth to approximately 100 AU. Turbulent viscosity plays a significant role in disk evolution, with values typically in the range of 1,000 square centimeters per second for a solar mass system. For a system with angular momentum of approximately 200,000 gram centimeter squared per second and a mass of 1.1 solar masses, the accretion stage lasts approximately 100,000 years. As the system evolves, it enters the class 0 phase, characterized by a dense envelope still collapsing onto the central protostellar embryo. This stage begins approximately 100,000 years after initial formation, with the protostar deeply embedded within its parent cloud. During this critical phase, more than 50% of the final stellar mass is acquired by the protostar from the envelope, with accretion rates exceeding 0.001 solar masses per year. This accretion process generates sufficient energy to power strong outflows and highly collimated jets, which are hallmark features of Class 0 objects. These outflows break out at the rotational poles, reversing the infall and producing distinctive bipolar structures. The powerful outflows play a crucial role in the overall evolution of the system, clearing paths through the envelope and redistributing angular momentum. The system subsequently transitions to the Class 1 phase, marked by a significantly thinner envelope that allows the first stellar photons to escape, resulting in increased infrared luminosities. This phase represents an intermediate stage where the protostar is still accreting substantial amounts of material, but has already accumulated most of its final mass. By the end of the combined Class 0 and I phases, approximately 99% of the final stellar mass has been accreted, though the disk itself continues to evolve and grow. During these early evolutionary stages, mass transport through the disk is remarkably efficient, with evidence suggesting almost an order of magnitude difference in mass between Class 0 and Class 1 disks. This rapid transport may be facilitated by disk instabilities, particularly gravitational instabilities arising from the relatively high mass fraction contained in the disk compared to that accreted onto the protostar. These instabilities can lead to sporadic bursts of high accretion that effectively self-regulate the disk mass. Such episodic high accretion events manifest as FU Orionis-type outbursts, with estimates suggesting a typical low-mass star may experience approximately 10 such events during its formation. First identified by Herbig in 1977, these dramatic events involve temporary increases in accretion rates by several orders of magnitude. The presence of these outbursts provides compelling evidence for what has been termed punctuated evolution during the early disk stages. Early disk evolution is strongly influenced by magnetic fields, which play a crucial role in regulating disk sizes. Observational evidence, including small disk sizes, typically less than 60 AU, and detection of magnetic fields at all scales in protostellar cores, supports a formation scenario where magnetic braking affects the early evolution of disk dimensions. Recent studies by Mori, Sheehan, and Tsukamoto have highlighted the importance of these magnetic effects in explaining the observed characteristics of young protoplanetary systems. Additionally, observations have confirmed that a significant portion of the gas reservoir in the parent protostellar core undergoes efficient angular momentum reduction when transported to disk scales, consistent with the expected effects of magnetic braking. Studies by Galametz, Cabedo, and Gupta have provided observational confirmation of these processes. By the conclusion of the Class 1 phase, the envelope has completely dispersed, marking the effective end of the star formation process and the transition to a truly protoplanetary rather than protostellar disk. The system enters the Class 2 phase, becoming optically visible as a T Tauri star for low-mass stars below 2 solar masses, or a Herbig A-B star for higher-mass young stellar objects between 2 to 10 solar masses. During this mature evolutionary stage, the disk contains only a few percent of the central star's mass, typically with a much reduced accretion rate below 0.0001 solar masses per year. At this point, the central protostar has reached a surface temperature comparable to a main sequence star of equivalent mass. The protoplanetary disk now serves as the foundation for potential planet formation, with its properties establishing the baseline for core accretion models of giant planet formation. During the Class 2 phase, disk evolution is governed primarily by viscous processes rather than infall from the surrounding envelope. The specific mechanism generating viscosity in these disks has been debated, with magnetorotational instability, MRI, being one of the leading candidates, particularly in regions of sufficient ionization. The viscous evolution redistributes angular momentum outward while allowing material to accrete onto the central star, gradually altering the surface density profile of the disk. Simultaneously, the dust component undergoes significant evolution, with grain growth, settling, and radial drift all playing important roles. Small dust particles initially well mixed with the gas begin to collide and stick together, growing from submicron sizes to millimeter and eventually centimeter scales. This growth is evidenced by changes in the spectral energy distributions of protoplanetary disks and by direct millimeter wavelength observations. As dust particles grow, they also begin to settle toward the disk mid-plane due to the vertical component of the star's gravity no longer being fully counteracted by turbulent mixing. This settling creates a more stratified disk structure, with larger particles concentrated near the midplane and smaller particles remaining at higher altitudes. As particles grow beyond certain sizes, they begin to decouple from the gas and experience headwind, causing them to lose angular momentum and drift inward. This radial drift, often called the meter-size barrier problem, potentially limits the growth of solids in the disk and represents a significant challenge for planet formation models. Various mechanisms have been proposed to overcome this barrier, including particle trapping in pressure maxima or rapid growth through sticky collisions. The Class II phase also witnesses the emergence of various disk structures, including rings, gaps, spirals, and asymmetries. These features, increasingly revealed by high-resolution observations from facilities like ALMA, may result from a variety of mechanisms including embedded forming planets, disk instabilities, or the influence of magnetic fields. The presence of these structures plays crucial roles in the planet formation process, potentially serving as dust traps that concentrate solid material and facilitate the growth of planetesimals. As noted in research, the emergence of pressure maxima in the disk likely trapped dust on million-year timescales, allowing planetesimals to form at distinct times without significantly altering their isotopic properties. The final phase in protoplanetary disk evolution is the dispersal stage, during which disk material is either accreted onto the central star, incorporated into forming planets, or ejected from the system. Multiple mechanisms contribute to this dispersal, including ongoing accretion onto the star, photoevaporation driven by radiation from both the central star and external sources, agglomeration of material into planetesimals, and dynamical interactions with companions. Photoevaporation becomes increasingly important in the later stages, as energetic photons from the central star heat the disk surface and drive thermal winds that gradually erode the disk from the outside in. For disks in cluster environments, external photoevaporation from nearby massive stars can substantially accelerate this process. The interplay between photoevaporation and viscous accretion leads to a characteristic two-timescale behavior in disk dispersal, with a relatively long phase of gradual evolution, followed by a rapid clearing once photoevaporation dominates over accretion. Observational studies of disk frequencies in young stellar clusters indicate that the typical protoplanetary disk lifetime is approximately 3 to 5 million years, though with considerable variation. This stage typically spans up to about 10 million years in total, though the oldest discovered protoplanetary disk has survived for approximately 25 million years. Studies of transitional disks, systems with inner holes or gaps suggesting partial disk clearing, provide valuable insights into the disk dispersal process, potentially revealing systems caught in the act of forming planets or undergoing inside-out photoevaporative clearing. These transitional disks, representing approximately 10–20% of the total disk population in nearby star-forming regions, may represent an intermediate evolutionary stage between full protoplanetary disks and debris disks. The timing and details of disk dispersal have profound implications for planet formation, as they determine the window of opportunity available for planets to form before the reservoir of building materials is depleted. In our own solar system, the protosolar disk appears to have been quite typical in terms of size, lifetime, and dust behavior. Cosmochemical evidence indicates that high-temperature condensates like calcium-aluminum inclusions, CAIs, and amoeboid olivine aggregates, AOAs, formed near the proto-sun before being transported to the outer disk. Paleomagnetic data in meteorites suggest that the protosolar disk disappeared after approximately 5 million years, consistent with typical lifetimes observed for protoplanetary disks around other stars. The evolution of protoplanetary disks represents a remarkable journey from diffuse interstellar material to the organized architecture of stellar and planetary systems, beginning with the gravitational collapse of a molecular cloud, progressing through the embedded protostellar phases, maturing as a T Tauri system with an actively evolving disk, and finally dispersing through a combination of accretion, photoevaporation, and planet formation. These disks undergo a complex series of transformations over their multi-million-year lifetimes. Understanding this evolutionary sequence is essential for comprehending the origins of planetary systems, including our own solar system. The study of protoplanetary disks connects the fields of star formation, disk hydrodynamics, dust evolution, and planet formation, providing a coherent narrative of how planetary systems emerged from interstellar material. As observational capabilities continue to improve, our understanding of these fascinating objects will undoubtedly deepen, revealing new insights into the processes that shape the diverse planetary systems we observe throughout our galaxy.